Good morning, everyone. So this video is a pre-lab discussion about the Khp lab determination. So this should be the first video that you watch, and I'll guide us through the importance of the lab and what kind of you'll be seeing, and then you'll watch after this the actual video that has the experiment in it, and then another little video that has some post-lab discussion on it. All right, so let's go back to chapter 4 when we talked about acid and base reactions. What's significant about them? So if I have, here's my acid-base reactions. So let's just think very, very generically, an acid-base reaction that we see a lot. Hydrochloric acid and sodium hydroxide. And what products would they make? What's significant about an acid and a base reaction? Well, an acid-base reaction always forms water and a salt, an aqueous ionic compound. The hydrogen forms with the hydroxide of the base to form water, neutralizing. So this is actually a really important concept and is used a lot in chemistry to figure out different molarities of acids and bases, knowing that they reach that neutralization point together. Now, before we get a little bit deeper into that conversation, let's think about what makes an acid an actual acid. So if we think the structure of hydrochloric acid looks like this. Now, in a monatomic acid, it's really easy to see that this hydrogen makes this substance acidic because the hydrogen associates in water to then form with a base and make water. Well, what about a diprotic acid? So when you have two hydrogens. So take a moment and let's draw the Lewis structure of sulfuric acid. So it makes sense that sulfur will be this central atom. And I have my 4 oxygens around. I already know that my sulfate by itself has 2 double bonds and a single bond to be stable. So then my hydrogens have to be on the outside of my structure. Now, this is because it's an acid. It wouldn't make sense for the sulfur and the hydrogen to make bonds for multiple reasons. One, in order for a structure to be acidic, the hydrogens are making that structure acidic. So they want to dissociate easily in solution. And they will be attached to the more electronegative element. Now, how can I fix this structure? What do I need? I need to complete my octet by filling in my electrons. Now, I'm not going to actually draw the resonance here. But would I have resonance in the structure? Technically, you could have the hydrogens on the other oxygens, right? And then the 2 on the left and right would have the double bonds. Perfect. So this brings me up to specifically our structure today. So in this lab, you'll be focusing on Khp, which is short for potassium phthalate. And a lot of the times you'll see Khp, but it's actually KHC8H4O4. But instead of always having the whole formula written, a scientist or people around just say Khp for potassium phthalate. And this is a weak acid and reacts really well with base to neutralize solutions. Let's look at the structure of that. Structure looks something like this. We have a carbon benzene ring. So this, you can see, I have 1, 2, 3, 4, 5, 6, 7, 8 of the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. No, just 5 of the hydrogens, because 4 and 1 more here, 5. 1, 2, 3, 4 oxygens. Where's my potassium? Well, what I drew right here, this is my phthalate. This is my HC8H4O4. Since potassium has a charge of +1, what does this structure have a charge of? Minus. Now take a moment to tell me which one of these atoms in this structure has a negative charge. So remember, that comes from formal charge, and formal charge is found by number of valence electrons minus the non-bonding electrons plus 1/2 of the bonding electrons. Which one of these has the negative? It's this one right here, this oxygen. You have 6 minus 6 non-bonding plus 2/2, which is 7, which gives you a -1. So, to make this KHP, there's your potassium, which acts as a counter ion with the HP, the phthalate, to make the compound electrically neutral. Now, which one of these are the acidic hydrogens? Well, which one is the most polar? That would be your most acidic hydrogen, just like this. So for a hydrogen to be acidic, we want it to be strongly attracted towards the most electronegative element, making it polar, which would be this hydrogen. Now, that doesn't mean that these aren't acidic hydrogens as well. These are also acidic hydrogens. However, since KHP is a weak acid, this bond right here makes it the most acidic hydrogen. When reacting with a strong base, though, it'll most likely dissociate. It can dissociate after further dissociation, all of the hydrogens. But at first, you can only ever lose one hydrogen at a time. So instead of saying HC8H4O4 minus, we say this is HP minus. So in this reaction, what we'll do is we're going to react with a base to neutralize. But why do we want to do that? So we have this KHP, and what's happening is you're going to be given an impure compound of KHP. So I'm going to erase my stuff up here. And in this lab, you'll be given a little vial, plastic vial, right? And it has some kind of solid in it. This is an impure solid. It has KHP plus an unknown. Now, you don't know how much KHP in this solid. You get this white powder, which you would see if we were able actually to physically do this lab. But you're going to see this white powder, and some of it is KHP and some of it is some other stuff. Your goal for this lab is to determine the percent KHP in your sample. Now, how can you determine the percent KHP of something? Let's say percent mass to be really specific. How can I figure out the percent mass? Well, in order to get percent mass, I would want the grams of KHP over the grams of my impure solid completely times 100. That's going to help me isolate just KHP from my entire solid. Okay, so here's the goal of my lab, my entire lab. Awesome. Now, how do I get there? So, for this equation, I need two components. I need the mass of my KHP, and I need the mass of my impure solid. how can you find the mass of the impure solid? Can you do that? Yep. Well, if you're given your whole vial right here, can you measure the mass of it to find out your mass of your impure solid? Yep. So we have that already. That's pretty easy to find because we're just going to take the weighing by difference, which I'll talk about a little bit more in a second when I talk more about the steps in the lab, and get the exact mass of my impure solid. How am I going to determine, though, the mass of my KHP? This is where titration comes into play. Since titration is an awesome method to help neutralize an acid and a base, we can determine different quantities to help us use stoichiometry and find moles. Now, we know the structure up here. The base that we're going to use is NaOH, and we are going to react that with, in a titration, with NaOH. So let's, while I erase this, take a moment to write that reaction. Now you can use the long name or you can use KHP. So we have K. I'm going to write the whole thing out, but you don't have to. You could write KHP. KHCAH4O4 plus NaOH. How is this going to react with sodium hydroxide? Well, we know that this is the K plus, and this is the HCAH4O4, right? And this hydrogen is what will react with the hydroxide. So I have my H2O that forms. And then I have this will then be minus once the hydrogen comes off, which will react with the sodium phthalate, plus potassium ion. Now, what would be significant in this reaction if I kind of want to simplify this so I know exactly what's reacting together when I do this experiment? Great way to do that is let's write out my ionic equation. Potassium ion plus, this is a weak acid, so it stays together, plus my weak acid, plus NaOH. Since this is a strong base, it dissociates completely. Water does not dissociate since it's a liquid. Now let's see, what are the spectator ions? Well, potassium for sure, and sodium. So I'm looking at phthalate reacting with hydroxide to make water and my anion. So this is kind of like your HP, right? And then this is your P minus. Awesome. So now we know that this is what's going to happen when we react them together. But how exactly does a titration work? So a titration helps you determine volume. How does it do that? So if we scroll down here to my little picture, here's an example of a titration. This is called a burette. So something that we've already seen. Inside we have a titrant. And in the flask we have something called an analyte. So what you'll be doing is we place NaOH in the burette of known molarity, exact molarity specifically, and KHP in the flask. Well, if they're both clear at first, how can I determine when the reaction is done, and why do I care about that? Well, I know, based off of my equation here, they're going to react together to form water. Since I have this equation, what can you use a balanced equation for? you can use a balanced equation for stoichiometry. Since I want, in the end, grams of Khp, how can I determine grams of Khp? Well, if I know always molar mass of Khp, grams over moles, I need moles Khp. And if I have a balanced equation, I can find the moles. But since I don't know what I'm starting with, I am looking for finding the moles of my base from my titration. Since a titration can help you determine the volume needed to form that water to neutralize the reaction, you can then use the volume and molarity to find moles of base to then find moles of acid. So this is how that happens. You have your sodium hydroxide, which is of known exact molarity because you standardized it if you did this experiment. Then you titrate it. Well, what you do is you take your Khp and you dissolve it with water. It doesn't matter how much water because we're not looking for concentration. We're only looking for moles. And the important thing is that you're also adding in something called indicator. Now, there's a bunch of different indicators out there. The ones we would be using for this reaction is potassium phthalate because it's colorless in acid and pink in base. So when you add indicator into your Khp solution, it's going to be clear like what you see here on the bottom. However, once you add base and it's basic and it neutralized, it would be pink. So what your process is while you're titrating is you begin to open up your little valve and slowly add in drop by drop some sodium hydroxide and swirling the entire time as you do so. Once your solution is pink for 15 seconds and doesn't go back to clear, you have reached your endpoint. Your endpoint means you formed your water and salt. The moles of acid and base are equal. The reason this is important is because now you can go back and use your stoichiometry to find the amount of moles of acid you have. What's important in a titration is you will be given, let's say you start right here, right? This is your volume initial. And then here you can see your volume final. So you calculate the volume difference because that's what actually goes into your flasks of the final volume minus the initial volume. If you have volume and molarity of the base, you can then calculate, since this is moles over liters, and this will be in milliliters, you can find moles of base, which you then apply to your stoichiometric equation to find the moles of acid. So that's the whole point of the experiment, because once you have your moles of acid, you can use the molar mass and find the moles, the grams of the Khp. Now, just a little bit, I'm going to talk about the different days of the experiment since we actually physically can't go and do it. But the experiment is set up in 3 different parts, and there's some important conceptual parts as to why that I wanted to talk to you about today. So day 1 of the experiment is actually to make Khp known. So since you'll be given an unknown and you won't know exactly what volume you need to titrate, and you want to know the exact moles needed to neutralize, you need an exact molarity of NaOH. Well, NaOH is actually a secondary standard. And what that means is that it's hard to know the exact molarity of NaOH that's pure by itself. This is because NaOH absorbs a lot of moisture from the air and reacts with carbon dioxide in the air. This makes it really hard to get the exact molarity of NaOH when you just make it by yourself. For this reason, we want to standardize NaOH using a primary standard. Since our end goal is to find the moles of Khp exact, we need to know the exact molarity. Since we don't and can't of an NaOH because it's a secondary standard, we have to standardize NaOH. And this is part 2. So in part 1, you're using Khp and making it to then standardize NaOH in part 2. So you'll be given a known amount of Khp to make a solution. Khp is a primary standard. It is easily measured, and it's really easy to know the exact amount of moles. It's a very stable powder that does not react with the water from the air and therefore can be used as a primary standard. So your first step in this lab is to make this little solution right here so that you have Khp to titrate with. I know that in the picture it's sodium chloride, but we're going to say this is Khp. Well, you want to make (250 milliliters) of a 0.10 molar Khp solution. Now this is all that I give you. This is in day 1. If you would come to the lab, I'd give you some time after my little spiel to tell you I want you to know how much you need to make a 0.1 molar solution that's 250 milliliters. So you'll be given a vial, again, with the Khp solution. And you want to make 250 milliliters of 0.1 molar Khp. Now, how can you do that? Can you figure it out? Well, we know that we can take the solid and dissolve it in water to make a molar solution. Well, if I'm given a vial with a bunch of mass, I need to know exactly how much mass to weigh out. So this calculation will be working backwards. So take a moment, if you can, to pause it here and calculate for yourself, if you were to actually physically be able to do this lab, how much Khp you wanted. Hopefully you paused it, and let's see. Since I know that this is mole over a liter, and I know I can get grams physically, I need to work back and use my molar mass. So if I take my 250 milliliters, divide by the conversion to get liters, then divide by multiply by my concentration, that's my goal, I get moles. Then if I want grams, I can multiply the whole thing by my molar mass of Khp. Now, a lot of the time, students actually just do Khp instead of doing the KHC8H4 O4. So make sure that when you're doing the molar mass, you're using the actual Khp, not just the abbreviated. So if you plug that in, you should get 0.25 times 0.1 times 204.22 is around 5.1 grams. So then, in order to make your standardized Khp, which is the first day, you transfer the contents into your dry weighing bottle. Now, this is where weighing by difference comes in. So you're given this vial that's plastic, and you want to first transfer the contents as much as you can into this little glass vial from your drawer. And you take the mass of that. Let's say this is your analytical balance. So you're not measuring anything. You are taking all of the contents from your plastic vial into your clean, dry weighing bottle and taking the mass. Then what you do is you take out some of it and weigh it again until you get around 5.1 grams. Now, the reason this is weighing by difference is because you are not leaving the vial on the analytical balance and constantly scooping sample into it. You are putting all of your sample into the vial. You didn't even measure the vial by itself. You then measure the vial with the sample together and you get some kind of a number. Then what you do is you take some out. You don't measure how much to take out and you weigh it again. The difference between these will be your mass of sample. Now, if it's not 5.1, what you would do is you would take some more out and weigh it again and subtract to figure out the exact amount that you have. You would keep doing that process, weighing by difference, until you got your amount of Khp that you wanted. Then what you're going to do is you then place your contents into your volumetric flask and add 50 to 75 milliliters of water. Now, it actually doesn't matter what range of 50 to 75, not 750, you add, because we don't care about concentration, right? Since we want moles specifically, it doesn't matter how much water you're adding. So then you would add up, I would say, about halfway, and then you'd stir it until you can see most of the Khp dissolve, and then go up to the line so that you know you have 250 milliliters total. Then you want to calculate your actual concentration. So remember, you may not have gotten exactly 5.1 grams. You may have gotten 4.9876 because you always want your total amount of sig figs. You'll see on that chart that you're given 3 trials. So this was trial 1. You're going through the day 3 of this lab, but you would be given your mass 1, let's say that was the analytical balance, mass 2, and then mass Khp. This would be for day 1, which we don't have a sheet for because we're not doing this part. So then let's say your mass was 4.9876, right, for precision numbers. I want to use this mass to calculate my actual concentration because the 0.1 was if I had exactly 5.1 grams. So then you would calculate your concentration and clean everything up, and you'd be done with day 1. So now day 2. Standardizing. Well, let's keep it in part 2. So now that you have this standard, you want to standardize NaOH so you can get the exact molarity. We're giving you the molarity on your sheet that you can see, but let's just pretend that you don't have it and we physically had to do it. So this would be through titration. So you're given, in this lab, you would have a bottle in the hood that has NaOH, but the molarity is not on it, and that's what you want to determine. So you have your burette, and then you will have Khp on the bottom. Now, we already slightly talked about this. You'll add NaOH into your burette, and you'll add Khp, water. Oh, you don't need to add water. That's for the third day, I mean. Khp and indicator. The reason we don't have to add water is because you already have water with your volumetric flask. So from your 250 mils up here, you take out 25 mils 3 times and place them into a flask with indicator. Now, what's really important before you start your 3 titration is to make sure you prime your burette and your pipette before you start your experiment. You then add NaOH into the burette, add the Khp and indicator into your flask, and you titrate, which means you would add enough volume to the Khp until the solution is pink. Now, you do this 3 times, 3 titrations. You would keep going until you have a 0.5% precision. So that means that you have a really, really, really small error. The way that you can calculate percent precision, which you would also do for day 3, is, let's say, for example, you calculated your molarity. You can also do this with volume. You have 0.1019 molar for trial 1. Let's actually say 0.1012 molar, 0.1013 molar, and 0.1019 molar. So you did these 3 titrations, and you can kind of see that that last one is not as close as your first 2. So in order to see if you're close enough in percent precision, what you do is you calculate your average, which is 0.1015 molar, and you use the largest and smallest number, the last trial and the first, and the average to find your percent precision. So 0.1019 minus 0.1012 divided by the average times 100. That's equal to 0.7%. You want 0.5, so you would have to continue another trial until your percent precision is around only 0.5 or less. So then you standardize with 3 titrations, and then you would calculate your molarity of your NaOH. How do you do that? Well, from this data, you would know the molarity of KHP. You know that you have 25 mils of KHP, and you would know the molarity. Let's say it's 0.1 molar KHP. You also know your volume of NaOH, and you want the molarity of NaOH. How can you determine that? Back to your equation, we know that the stoichiometry of the two can help us determine how much of the acid and base moles was needed to neutralize. So you can take the volume and molarity of KHP, right? What is the mole to mole ratio of the acid and base? 1 to 1. And then, once you get your moles of your base, you can divide by the volume of the base to get the molarity. So then once you would do this in day 2, you then know the exact molarity of your standard NaOH. Then we get to part 3, unknown KHP. Alrighty, so now in the 3rd day, you'll be given, again, a sample of an impure solid. And you want mass percent KHP. So you want the grams of KHP over gram solid times 100. We already talked about that you can know the total mass of your sample because you just weigh it by difference. So we're looking for the mass of KHP. Well, now you go back to your titration, right? So what you'll do is you will take your solid once you weigh it by difference, now, since you can't calculate how much you want on your vial, there's a number of your goal of mass. And then think about it. If you have, let's say this was 5.2 grams on your vial, right? And you want to make sure that you can do 3 good titrations. But you don't know if you're going to exactly have 3 good titrations on your first 3 trials. So let's say you want to do 5, just to be safe so you have enough sample. So do you want to weigh out the 5.2 and then dissolve all of that? No. So your goal is to weigh out your entire sample and then divide that sample up into 3 different measurements. That's one way. Or what you could do is dissolve the whole thing and then you just use the 25 milliliters like you did in the 2nd day. Once you get your KHP, You would then dissolve it in your flask, you would then add the water and indicator. And then you would titrate it with your known NaOH. You'll know the reaction is complete because you can then determine that the color has pink and it stayed pink, which means you've reached your endpoint and the moles of acid and base are, I'm losing my train of thought, are equal. There you go. So now that was the pre-lab and post-lab discussion, actually. We'll just keep it in one video. I know I said there'll be two, but I kind of did both in one. If you take a look at your data sheet, you'll see that you have 3 trials, and this will be for the 3rd day. So this is pretending like we've already done the first 2, which was kind of prepping for the 3rd day. And you have 3 trials. So in the first couple boxes, you'll see that you have the mass of your weighing bottle with the sample, and then the mass after you took some sample out to know the exact mass of sample that you have. You are given your initial and final volumes of sodium hydroxide, and then you'll see that you want to calculate the amount of Khp, and you want to calculate the percent precision, which we've gone through how to do both of that. Before that part, you'll see 3 different little screenshots of reading a burette. So part of this whole lab was to make sure you can accurately read a burette. Something important is, we already discussed this in some of our previous labs, but we never start at 0.0 milliliters when using a burette because we want to be as precise as possible. So we always start a little bit below that. When reading a burette, you always want to go to the hundredths place, and you basically look at exactly where the meniscus drops down. So to help you with that process, take a look at these 3